Welcome to this e-lecture, which is about contingency table analysis. And what is really a contingency table, or what we will call a cross table? Well, a cross table shows the number of observations having a particular combination of values on two different variables. And in this cross table, you have the age group in the head of the table, 4 different age groups, and a variable showing the distribution, or the distribution about attitudes towards parents beating their children, and it's grouped into 3 categories. So it's 1 to 3 disagree, 4 to 7 which is kind of middle position, and 8 to 10, which is agree. So it's attitudes towards parents beating children by age then, for the United States, using the World Value Studies from 2010 to 2013. So this is a cross table. It shows the combination or particular combination of values for 2 different variables, in this instance age and the attitude towards parents beating their children. When we are doing bivariate contingency table analysis, we have to determine the dependent and independent variable respectively. And in our example, of course, attitudes are the dependent variable and age is the independent variable. And we have to calculate the contingent relative distributions for the dependent variable. And the contingent relative distribution is the distribution on the dependent variable given the values on the independent variable. And when you have done that, we look for statistical associations or association by comparing the contingent relative distributions. If the relative distributions are equal, there is no statistical association. It's statistical independence, but if the relative distributions are unequal, there is statistical association between the 2 variables. So in our example, we will examine whether there are differences between the age groups according to how they view whether it's justifiable or not for parents to beat their children. So we will look for attitude difference between age groups. So we have to decide what is the dependent and independent variable respectively. So the independent variable is the one that's supposed to cause or lead to variation in the dependent variable, and the dependent variable is supposed to be varying depending on or under influence of the independent variable. And in our example, it's quite easy to see that, okay, it's age that is causing differences in attitudes towards parents beating their children, or what we're going to test. But in other analysis, it's not so obvious. It might be, well, social background, personality, attitudes, and actions. There are many other. If we're going to include social background and personality, for example, what is what are the dimension there, or the timeline, really. It can be harder to tell what is the dependent and independent variable. But in our example, it's really easy. It's age which causes the differences in attitudes towards parents beating their children. That's because age comes before attitudes in time. Okay, so then you have the contingent relative distributions. And the contingent relative distribution is the relative distribution on the dependent variable for units with a particular value on the independent variable. And in our case, it's the age groups, which is the independent variable, and we look at the distribution on the dependent variable, which is the attitude for these different age groups. And then we compare the relative distributions. So we compare the relative frequency for a particular value across the contingent relative distribution, And if there are equal percentages, there is no association, and if there are unequal percentages, there is no association. And here we can see that there is actually there is a difference between the age groups, and we can see there is a difference between the age groups here and a difference between the age groups here. And of course, we want to test whether this is this a real difference, or is this difference due to our sample being very much different from the population we want to generalize to. And then we come into inferential statistics again, because it's all about inferential statistics when we do hypothesis testing. Well, it's concerned with the possibility of generalizing findings from a sample to the population. And probability sampling increases the chance of getting a representative sample, but does not guarantee this. Samples will usually deviate somewhat from the population, and some samples can deviate a lot. And there is always a possibility that a statistical association between two variables in a sample is due to chance, that is sampling error. And according to statistical theory, we can calculate the probability of getting a particular statistical association in a sample, given that there is no such association in the population as a whole, and that's our p-value. And if the probability is too high, and the convention is more than 5%, we cannot make the generalization that there is an association between the variables in the population, because the risk is too high that the sample association is caused by sampling error. So we have to be at least 95% sure, or even sure, that there is actually an association between the variables in the population, and that the association we found in our sample is not, we have to be 95% sure that this is not due to sampling error before we generalize to the population. So, hypothesis testing contingency table. When testing an association in a contingency table, we always test a null hypothesis, so no association. So our null hypothesis is there is no association between the variables in the population. If the null hypothesis is correct, the observed association is due to sampling error and does not reflect a real association in the population. And if the risk of getting the sample association, given that H0 is correct, is lower than the chosen significance level, usually 5%, we reject the null hypothesis, or H0. So that is, if the risk of if the likelihood of H0 is less, H0 being correct is less than our chosen significance level. So if the p-value is lower than our chosen significance level, we don't believe H0 is true, so we reject H0. We are 95% sure, or even sure, that H0 is not true, that there is actually an association in the population. And when we do when we test hypotheses using contingency tables or frequency distributions or cross tables, we use the chi-square test. And the chi-square test is based on making a deviation, or checking deviation between the sample's cross table, the actual cross table, and a corresponding table without an association. And the higher the chi-square, the less likely that this association is due to sampling error. And the chi-square automatically increase with larger tables, and must be corrected for degrees of freedom. That's reflecting the table size. And you calculate the degrees of freedom by taking the number of columns -1 multiplied by the numbers of row -1. Then you get the degrees of freedom. And the decision rule is statistical tables, they report critical chi-square values for the combination of degrees of freedom and significance levels. H0 is, or the null hypothesis, is rejected when the actual chi-square is higher than the critical chi-square. And the statistical programs always report the p-value, and that's based on the critical chi-square value. And we reject the null hypothesis when the p-value is lower than the significance level. So we can be more 95% sure or more, or even sure that H0 is not true. So what do you do? Well, what is the procedure? We state the null and alternative hypothesis. We choose the level of significance, usually 5%. We determine the appropriate statistical method, that is the chi-square test in our example. We calculate the p-value, and SPSS does this for us if we use SPSS and all other statistical softwares as well. We decide whether the null hypothesis can be rejected or not. And when we do this in SPSS, we choose Analyze, Descriptive Statistics, crosstabs, and we put in rows, we put the depend variable, which is the justifiable for parents to beat their children, and in columns we put the independent variable. We also have to go on cells and tick off for observed, and in percentage we have to using the percentages calculated by columns. We have to tick off for that as well, and we also have to go on statistics and tick off chi-square. And we test the following hypothesis. The null hypothesis: the distribution of attitudes towards parents beating children are equal in all age groups in the population. And we test the alternative hypothesis, which is the distribution of attitudes towards parents beating children are not equal in all age groups in the population. And the results are as follows. SPSS has found that the chi-square value is 57.49, and if you look in a critical table, you'll find that this is the p-value is much less than our chosen level of significance. So we reject H0, that there is no difference between the age groups in the population. We conclude that there is a difference between the different age groups in the population, using a chi-square test to test a hypothesis based on crosstabs. So that was the e-lecture on contingency table analysis. Thank you so much.